If we have a point charge Q, indicated right here, and if there are no other charges other than the test charge that we're trying to move around in the vicinity of Q, then it turns out that the potential difference, VAB, the voltage from point A to point B, voltage change from point A to point B, or the potential change, is just equal to KQ over RB minus KQ over RA. This potential change depends only on the point charge Q, the magnitude of that charge, and the distances RB and RA. If RB is less than RA, then the denominator here is less than the denominator here, and this term will be greater than this term. Then if Q is a positive charge, this term having greater magnitude than this term means that this is positive and larger than this one, means that the difference of these is positive, so the voltage between the 2 points, or the potential difference from point A to point B, is positive. That means that we would have to do positive work to move a positive test charge from point A to point B. And that's clearly the case. If Q is a positive charge, then it's repelling any positive charge we try to move in to a closer point. So we have to do positive work to move from A to B. Since we have to do positive work to move from A to B, then the potential difference from A to B has to be positive. We obtain these expressions, as you recall, by integrating the force times the displacement, or the distance, as we move a charge from a point A to a point B in the vicinity of this charge, and the details of that, of course, were indicated in the appropriate class notes. Okay? The potential function, then, for a point charge, we're going to call this potential function V of R is KQ over R. Okay, if we define the potential function V of R as KQ over R, then this difference, the potential from A to B, KQ over RB minus KQ over RA, is seen to be nothing but V of RB, and if we have RB here, then we have RB here, and we have V of RB equals KQ over RB, same as we have here, minus V of RA, which would be KQ over RA, which corresponds to what we have here. So that this potential function has the property that the potential difference from A to B is just the potential calculated at point B minus the potential calculated at point A. We subtract where we are from where we're going. The potential at the point that we start at, subtracted from the potential at the point where we're heading. If we have a bunch of point charges, then the potential function is just what we get when we add all the KQI's over, I should really have an R sub I here, over R sub I. Okay? And the idea here is simply that we add up all the KQ over R's for a bunch of charges. I is just the index of a charge, so we add up KQ1 over R1 to KQ2 over R2 and KQ3 over R3 and so forth for whatever number of charges we have. And R1, R2, and R3 are the distances of the point X, Y, Z from the location of the charge Q sub I. Now this is called the principle of superposition, or maybe results from the principle of superposition, depending how you define that principle. It says we just add up the potentials due to all the point charges at the point X, Y, Z. So that the potential at a point X, Y, Z is just the sum of all the potentials of the point charges evaluated at that point.